So we've got this context here, and that's going to go for the whole of the question. So Sarah releases a red car from rest. That's important, so we're going to underline that. Down a slope of a length of 0.5 metres. The car accelerates steadily, another important piece of information, and reaches a speed of 1.5 metres per second when it gets to the bottom of the slope. Okay, so we're starting at 0 metres per second, and we're ending up at 1.5 metres per second by the time the car gets to the bottom of the slope. Okay, so the first question is asking us, calculate the acceleration of the car as it moved down the slope. Alright, so what do we have? We have a VI. That's our 0 from rest, 0 metres per second. Okay, we have a VF. 1.5 metres per second. We have a distance of 0.5 metres, all right? And we're trying to work out an acceleration. So, if we have a look here, down here at our mechanics formula, we need VF, VI, A and D, okay? So we don't have any time, so we can't use these three, but we can use this one. VF squared equals VI squared plus 2AD. All right, so let's write that down. VF squared equals VI squared plus 2AD. Okay, so I like to rearrange with the letters and then put the numbers in once I've all rearranged it. So that's the way I'm going to do it. You can do it another way. All right, so we're wanting to get A by itself. Okay, so let's deal with VI first of all. Now this one does have a trick. So because VI is actually 0, in this case, we can just ignore VI altogether. It's going to be 0. 0 squared is 0. Okay, so our actual equation is going to be this. Okay, because VI is 0, VI squared is going to be 0, so we can just completely get rid of it in our equation already. Okay, this is a lot simpler now. All we have to deal with is this. Okay, so 2 times A times D. So what we can do with that is VF squared divided by 2D gives you the acceleration. Okay, so now that we've rearranged, we just need to plug the numbers in. So 1.5 squared divided by 2 times 0.5 metres. Okay, so let's put that in the calculator. 1.5 squared, okay, divided by, I can do 2 times 0.5 in my head, so divided by 1 is good, which we can also do in our head. So our acceleration is 2.25 metres per second to the negative 2. Now, we need to check our significant figures. So, we get given 3 significant figures here in our length of 0.50, okay? But we only get 2 significant figures in our VF of 1.5. So our final answer has to be also in 2SF. So 2.3 metres per second to the negative 2, because we're working in an acceleration. Okay, so that question is our achieved question. There's a bit of rearranging involved, okay, but it should be pretty straightforward. All right, so this next step, the bottom of the track, bottom of the slope, the track is flat. Okay, the red car is moving along with its speed, its velocity of 1.5, and it collides with a stationary, so V equals 0, blue car. Okay, helpful diagram. The mass of the red car is 0.05 kilograms and the mass of the blue car is 0.04. So in this we can already see that this is going to be a momentum question. We have masses and we have velocities and we have a collision, so it's going to be momentum. Okay, so part B. If the velocity after is 1.2, calculate the velocity of the red car after. So in our diagram, we're wanting to work out this velocity here. What is the red car doing after the collision? Okay, so first of all, we need to remember that it's conservation of momentum. So PF equals PI. So we'll just write a little note to ourselves up here. Okay, final momentum is equal to initial momentum. All right, so initially we have all that we need. We have two velocities, one for each car. All right, and we have two masses, one for each car. So our initial momentum is mass times velocity. Okay, now you can do the maths for the blue car, but because the velocity of the blue car is 0, anything times 0 is 0, so all we're going to need actually is the velocity and the mass of the red car. Okay, so the mass of the red car is 0.05 times by 1.5, and that gets us to an initial momentum of 0.075. Okay. So then we need to do our final one. So our final is going to equal our initial. So PF is going to equal mass of the red times velocity of the red plus mass of the blue times velocity of the blue. Okay. And what we're wanting to work out is this one here, the velocity of the red car afterwards. Okay, so we have all the other values. All right, so we can rearrange now, or we can substitute and then rearrange. All right, so what we're going to do is we're going to do PF minus, because we're moving this whole lot to the other side, so minus okay, and then we're just left with the momentum of the red car. Now we only want the velocity. Okay, so if you want to rearrange first, that is the way to do it. All right, so we just need to substitute in, so 0.075 minus the mass of the blue car, which is 0.04, times by 1.2, and that will need to go in brackets, all divided by 0.05. Okay. And we should end up with a velocity of 0.54 meters per second for the red car. All right. Now you can do this in one step. So instead of working this out separately and then putting it in here, you can just put this all instead of the PF and do it all at once. That is perfectly legitimate as well. Okay. So getting this all correct and getting to our final answer of 0.54 meters per second, we've just got a merit for this question. Okay. If the duration of the collision was 0.08 seconds, calculate the average force that the red car exerts on the blue car. All right. There are two ways to work out this, so I'll show you both. We've got a time of 0.08 seconds. All right, and we're wanting to work out a force. Okay, so what we're wanting to do is we're wanting to look at impulse. Okay, and on our reference sheet or our resource sheet, all right, impulse is change in momentum, which is force times the change in time. Okay, we're actually wanting to work out this force. But first we need to calculate the change in momentum. Okay, and this is the bit that you can do two ways. All right, so we can look at it from either the red car or the blue car's perspective. Okay, so if we look at it from the blue car's perspective first, all right, so to find out the change in momentum, we need our initial minus our final. But for the blue car, it has no initial mass because it was stationary. All right, so all we need is to work out its final momentum. All right, and that is simply mass times velocity. All right, so we have the blue car mass of 0.040 kilograms times by its final velocity of 1.2 meters per second. Okay, and that should end us up with 0.048 kg meters per second. Right, so this is option 1. Okay, option 2. This time we can look at the red car. Okay, so the red car does have an initial velocity, so it does have an initial momentum. All right, so what we can do is we can work out that change in momentum. All right, again, mass times velocity. So our initial momentum is going to be 0.05 times by 1.5 meters a second. That was the initial. All right, and then we're going to minus 0.05 times by the final velocity, which you worked out in B, which was 0.54 meters per second. Okay, put that into your calculator and you should end up with 0.048 kg meters per second. All right, so you've got the two options there. Okay, now that we've worked out a change in P, all we need to do is calculate the F, which is actually where we're wanting to go. So change in P equals F times change in T. So F equals change in momentum or impulse divided by change in time, which is 0.048 divided by 0.08. And that will give us a force of 0.6 newtons. Okay. All right, question D. On another occasion, the red car was going around a circular part of a track at a constant speed. Part I, name the force acting on the car and draw a labelled vector on the diagram above to show the direction of the force. So we've got two instructions. Name the force and draw a labelled vector on the diagram. Okay, so because we're going around in a circle, our force will be the centripetal force. Okay, and remember that that force is always acting towards the centre of the circle. Okay, so once the car gets to here, our FC will still be acting towards that centre of that circle. Okay, part 2. Discuss the effect of the force on the size and direction of the velocity of the car. The first thing about this force is it changes the car's direction, all right? It is constantly pulling or pushing the car towards the centre of the circle, all right? And if we remember from those, the tennis ball on the string, any of those examples, the car's instantaneous velocity at whichever point we take a snapshot is at a tangent to the circle, okay, so at right angles, all right? But that changes as we go around the circle. And the reason that changes is because of the centripetal force, okay? So that's our first point, looking at direction, okay? So the force is acting towards the centre of the circle. All right. Causing the change in the direction of the car's velocity. Okay. So we've talked about direction. We now need to talk about size. Okay. Now, does the car go any faster or any slower around this circle or around this track? The answer is actually in the question, all right? It's at a constant speed. Okay. So because this force is at a right angles to our instantaneous velocity, it has no effect on the size of the velocity, okay, or the speed of the car. How fast is it actually going? All right, so that's our next part. The force is at 90 degrees or at right angles to the instantaneous velocity. All right, so it does not change the size of the velocity or how fast the car is going. All right, so this is the excellence question. All right. For achieved, you needed the correct name here and the correct labelling, or you needed one of these effects to be correct. All right. For merit, you needed the name and the arrow plus one of these effects. And for excellence, name and the arrow plus both of the effects. All right, for size and direction. Okay.